lives, we've been taught that the world is four-dimensional. Over the next hour, we're going to discover there are 11 dimensions. Not only that, but we're going to figure out how to visualize and intuitively comprehend all 11.
So, let's see if we can make something else more clear.
Okay.
You already heard from our friend Matt about the 11 dimensions.
I heard about the book that you wrote, yes.
Yeah. I want to pitch the whole thing to you and basically just in the next hour get you to visualize and understand all 11 dimensions. Okay?
Wonderful.
Yeah. So I guess this is, first, I think we should review what, you were in physics before. What are the mysteries that you remember from back when you studied physics?
Well, first I remember being told that we can't picture more than 3, or if we had time, 4 dimensions.
Okay.
So already you've blown my physics professors out of the water.
Yep, that's definitely said we can't do that. And if we do that, then we did overturn everything. What are the biggest things that stand out like in sci-fi that are actually real things in physics?
Dark matter.
Dark matter.
Black holes.
Yeah, good. That's what quantum tunneling.
Right.
Time travel.
Right.
So all these mysteries are things that defy our intuitive sense of the world, which is why they're fascinating, which is why we're spending so much time trying to figure them out. But our explanations today so far only explain them mathematically, right? You can't even really go to the professional physicist and ask them, what is a black hole? And if they would try to answer the question, they're going to give you a whole bunch of mathematical explanations, pretend like only the elite that have a PhD in physics or math can understand the question. But it really comes down to it, they don't understand the answers.
Because you can't visualize it.
Yeah.
So they can't explain it to you in a way that you can see and understand.
And if you can't explain something that way, then you don't truly understand it.
Right.
So this is the goal. And the link that we have here is hinged off the whole claim that we all had as we read in physics or taught physics, that we can't comprehend or visualize more than 3 space dimensions. So we're going to do that.
Wonderful.
We're going to do that.
Should I order another cup of coffee?
Maybe. I want to go into a little bit of detail about a few of the mysteries so we can keep track of what the mystery is, what we're trying to solve. And then we're going to introduce other dimensions and get you to visualize other dimensions. And once we get that picture in your head, then we're going to go back and address the mysteries and see how it automatically solves each one of those mysteries. Okay. So one of the ones you mentioned were black holes. We'll start with that. Okay. What is a black hole? How would we define it today?
It's basically sucks in everything around it, and then everything just disappears.
Okay.
And nothing escapes.
Yeah, that's why we call it
light.
black. So
Right.
no light can escape it.
Right.
All right, so its gravity is so strong that at some point, some distance from the center of this thing, nothing can escape the gravitational pull, including light, so we call it a black hole. What a black hole looks like inside the Schwarzschild radius, inside the event horizon, is something that's, it's not even debated. It's just no one knows. Okay, there's just no real idea.
And the event horizon is the last thing that's visible?
It's that imaginary line where if you're just inside it, light can't even escape. If you're just beyond it, light can barely slowly escape. It's not an actual physical shell. It's just that imaginary line of where that transition happens.
The edge.
Yeah. What it's composed of is a big mystery. So now we have an object that we're claiming is by definition size 0.
With
Yet it
infinite
has
density.
infinite density because it's size 0. Okay, so there's some confusion already going on right there, and yet it still has mass. So, all that mass. There's stuff that's shot off, but we'll just talk about the stuff that's left over. All that mass is still there, which means the gravitational pull that it had before is still there. Yet it's something that's very difficult to comprehend. What is infinite density? Right? Why is a black hole? How did it get real infinite density? Why does it collapse to 0 size? What does it even mean? Why does time slow down as you approach a black hole? And this is something that's partly answered by Einstein's attempt to give a visual model of what's going on in space-time, but it's still only a partial solution. It was a really good attempt because there was no solution before that. We had Newton's picture of the universe, And it was an intuitive solution. It was a way to understand and describe how everything moves around, and it's the one we pretty much have stuck in our heads today.
So we go in stages. The name of your book is Einstein's Intuition.
Yeah.
And the idea is that it's an intuitive kind of conclusion or answer to the questions that he posed that
Yeah,
weren't
he was
yet
ultimately
answered.
searching. His intuition was that there is a picture, there is a map of nature, and we're searching for that map. He was definitely searching for that map. And once you find the map, you can read it and understand the rules of nature. And by understanding the rules of nature, as he put it, you were able to read the mind of God. You were able to connect to something far deeper than you connect to in your average life. And by connecting to everything, you satisfy that deep yearning we have for the whole quest, the whole human quest, understanding everything around us, understanding the things we encounter every day and the deep mysteries and how they all connect to each other.
to satisfy the void.
Yeah.
How lovely.
Yeah, so that's what we're doing. We're trying to find the new map. And now we're making the claim that the reason we haven't found the map is because we've been stunted by our belief that we can only visualize 3 space dimensions. So modern theories today are claiming mathematically that there are 11 dimensions. Since their claims are entirely mathematical at this time, and no one says, well, if this is the picture for the 11 dimensions, no one's been able to intuitively absorb this picture and then see what it means.
It just
So-
sounds like sci-fi. It's just a number.
Yeah, it's just a bunch of numbers.
Right.
So it's hard to translate into any kind of meaning. However, as we process it more and more through our computers, more things line up, and it gives us more and more confidence that, hey, that maybe this is really going toward what we're looking for. Maybe it's somehow actually explaining the map we want, yet we're never understanding the map that it is. So if we don't learn how to visualize the other the total 11 dimensions, then no matter how accurate, we can prove that this string theory, superstring theory, M theory, supergravity, whichever one you use is 11-dimensional. It doesn't really matter how accurate it is mathematically if it doesn't allow humans to connect to the picture. So that's the reason we need to do this. Another mystery would be quantum tunneling. What do you remember about quantum tunneling?
I have this picture of, for example, an electron captured in a box that it isn't supposed to be able to get out of. And it seems to come and go at will, or the process is untraceable. It's there, it isn't there.
Yeah, okay. So in the framework we all have stuck in our head, the intuition we were all taught to believe in about what nature is, if you have a ball, like an electron, stuck in a box, the ball can bounce around forever and just keep going. And once you seal the box, it'll just stay in there until you open up the box and let it out, right? These electrons that we put in boxes that they can't escape out of based on all the rules we would expect to be real, well, we find them escaping all the time, every time we do these experiments. So the best way to explain what's really going on, what appears to be going on, we could say, is that the electron doesn't go through the material at the edge of the box. It doesn't go through the wall. Okay? It doesn't tunnel between atoms and then come out. It actually disappears from space-time. Somewhere inside the box just disappears and reappears in space-time somewhere else, which could be back inside the box, or it could be outside the box, or it could be stuck right in the wall, and then it's just trapped. Okay? And this sort of thing we measure in the lab. We got all kinds of fancy equipment to measure all these kind of quantum mechanical effects, but you might think that they don't really influence our day-to-day lives. Okay,
Right, it
you
sounds like
don't
Star
see
Trek.
things. Yeah,
Yeah.
you never see something big just disappear and then reappear somewhere else. This stuff definitely affects our modern lives because modern technology is heavily dependent on these processes. So our transistors, our entire computers would not run if they didn't rely on this quantum tunneling effect. Radioactive decay is quantum tunneling. So the lifespans of stars depends on this effect. So it's a very vital thing, and it's absolutely confusing. I mean, what does it really mean to say that something like an electron disappears from space-time? Where is it?
It doesn't work on our Newtonian big
Yeah,
map
you
model
can't actually
at
answer
all.
that question, right?
No.
Which is why quantum tunneling has stayed absolutely mysterious. So in order to track or to talk about quantum tunneling, we're forced to just statistically explain what's going on. You could say out of 10,000 electron trials that you watch them go, this many make it outside of the box and this many don't.
So we enter the realm of probability
Yeah.
rather than predictability.
It becomes our only way to explain it.
Right.
Is it because there is no inherent cause to what's going on? There's no cause and effect that allows you to trace what's actually going on, like you can in the big world, the macroscopic world? Or is it that on the small realm, we're losing vital information?
So it appears to be inexplicable. It appears to be sci-fi, but it's just that we
Yeah.
can't see. We don't have all of the information
Yes.
to explain it.
If there really are only 3 space dimensions and 1 time dimension, then all quantum mechanics, all the effects that quantum mechanics tries to explain are pure magic. Okay,
Right.
they're unexplainable. You can never understand them. Okay, this is one of the popular interpretations, even in physics right now, of what nature is. It's something that can't be understood. Einstein believed something entirely different. He believed that the reason we have effects that are mysterious to us right now is because we don't have the whole picture. And if we did have the whole picture, which was the ultimate goal, okay, I mean, it's the entire quest of his life. If you find that whole map, you now can connect to something that's much richer, much deeper than anything we had before. We can actually align our intuitive sense of what nature is with what nature actually is.
And that way it would explain all of
Yes.
the mysteries.
Yeah, mysteries naturally go away when you see the magician behind the curtain.
Right.
Right? Which is exhilarating. I've expressed this to some people and they, well, wouldn't that take away the whole value of it? And I see their argument from some point, but I see it being the exact opposite. You know, just because you've seen a rainbow from Victoria Falls doesn't mean now you no longer like rainbows.
And we'll
Right.
always have the mystery of love.
Yeah. Being able to connect to the mysteries is the most valuable part. So here we are trying to actually get a map that allows us to connect to mysteries. Things that we're missing right now. Things that are going on all the time in everyday life, every single second, at every place in the universe. We're entirely withdrawn from. And we can really tap into all of that if we can solve all these mysteries. Okay, I'll run through a little faster just to give some kind of hint of some of the other mysteries we need to do. Like, what is time?
Time is that convention that keeps everything from happening all at once.
Okay, that's as good a definition as any, right? In
Don't know.
physics, we haven't been able to define time. Okay, there's this loose sense. Everybody knows what time is, but nobody can define what time is. So in a way, we use a vague conception of time to go about our lives. And that vague conception is instilled in our intuitive sense of what nature is. But nobody can define it. And without being able to define time, and time being one of the major aspects of the universe, you can't really even claim to have a map, right? I mean, it's like one of the vital parts of that map. Imagine if there's no time, there's not really a map to explain anymore. Because in a higher dimensional model, map of space-time, of nature, we gain a clear definition of what time is, and we also gain access to a whole bigger picture. Time is one of the ones we have to define.
Okay.
We have to try to understand, okay? And in some ways it's a shock that we don't know what time is, okay? Another one would be, say, matter, light, energy. What are those? Okay, extremely difficult to actually
Light
define.
is a wave and particle something.
Yeah,
They
okay,
don't know.
we try to answer the question by describing properties of the thing we're trying to understand, right?
Right.
So light is something that has the property of being a wave, has the property of being a particle, depending on which property you're looking for. Okay, so it's either it has both all the time, and whenever you set up an experiment to test its particle properties, you find its particle properties, and if you set up an experiment to find its wave properties, you find those. Or it's flip-flopping back and forth, somehow tricking you. Every time you're looking for the one that happens to be that one. It's this big mystery. It's particle-wave duality. What actually is it? What is the thing that's acting as a wave and a particle? Why can something be simultaneously a wave and a particle? I mean, there's a whole central mystery about light.
So these very important concepts or components of physics aren't really defined.
They're very loosely defined, and they're all approached from the old Newtonian conception that we all have in our head, that intuitive, three-dimensional Euclidean space that we all have stuck in. That's how we frame our questions. And if we're starting from that understanding, it's really hard to jump to a higher level of understanding when you're asking all these questions. These things just stay mysteries. like in Edward Abbott's Flatland. If you're viewing everything in 2 dimensions, when a carrot falls through your view, you can come up with a lot of fascinating explanations of what it was and why it just appeared out of nowhere and then disappeared into nowhere. But you really can't grasp what's going on without jumping to a higher view. Okay, so there's a handful of them. We got a whole bunch of more modern ones, dark energy and dark matter, Heisenberg uncertainty, and all these things end up being related. Okay, when you study them or read about them, you wouldn't get any sense that they're related. I mean, what does a black hole have to do with Heisenberg uncertainty? Black holes are huge, yet zero size, right? Their effects reach out light years, and their size in the center is supposed to be 0. So what does that have to do with?
It's hard to wrap our brains around that.
Yeah, it really is, because we're starting from conceptions that require we stay in the model of 3 space dimensions.
Right.
So by
we're
wrapping our
limited.
brain around it, we're dancing circles in our brain with contradictions because we're sticking in a system that is full of contradictions. Nature cannot be 3 space dimensions because nature can't inherently support contradictions. It wouldn't be contradictory.
Oh, wonderful. So jumping up in dimensions creates this resolution of contradiction.
Yeah,
Our
exactly.
brains will be so happy.
So so that we discussed a little bit about the small world. In the small world, nothing makes sense intuitively, right? It's all Harry Potter magic and fascinating and exciting, and we want to understand it because it is those things. And if you get a little access to what's going on intuitively, intellectually, be able to visualize what's going on in the small world, that's really exciting. Well, the big world, though, we might assume is, well, we got a good grasp on that. We understand the big world, right? Well, we don't, because we have that thing called a warped space-time, right? This is where Einstein came in, and he explained it's not Euclidean space. It's not 3 space dimensions that are just consistent and smooth everywhere. The texture, the structure of space-time changes. He called it curvature. And it changes dependent on mass and energy. So if you approach something that has a lot of mass, a black hole, a star, even the Earth, then the curvature of space-time changes as you approach it. And this curvature leads to a whole bunch of effects. But the fact that the curvature exists tells us that there's something wrong with the geometry we were assuming that we were framing our question with to begin with.
Right, that was predictable and linear.
Yes.
So the curvature, is this that image that we see of the sort of trampoline that's stretched?
Yes.
The fabric, checked fabric that's stretched in
Exactly.
a direction.
So, and that's a valuable picture, right? And we've seen it lots of places. Those are like a black holes in the middle of that picture, and things are orbiting around, so it looks like they're just following, just right along the circle on there, and everything's happy because it seems to give you an explanation for why it's doing it. Okay. There's some problems though, because it doesn't really intuitively connect you to what's going on. In that picture, the black hole's in the middle, right? And it's stretching down.
Right.
Why is it stretching down?
Because it's curving space-time.
Yeah, because it has mass.
Right.
And its weight is pulling down the space-time, right?
Okay.
Okay, so visually, you're assuming there's a weight to the black hole
Right.
that stretches space, and we're using that weight to explain gravity. But weight is a function of gravity. Okay?
Right.
Weight is mass times gravity.
Right, exactly.
So we're using the pre-existing gravity in our head
Uh-huh.
in that downward direction in that model to explain the
Explain.
existence of gravity, which doesn't explain anything.
Right.
Okay, another problem is that plane that we're stretching, we took that plane very deliberately. We said, let's take a random slice of space-time, a flat Euclidean slice all the way through the universe, okay? And you could go any direction you wanted. We're just taking one random direction, just whichever one we pick. And now we're going to put that plane flat in our field of view, and we're going to put a whole bunch of imaginary grid lines on it.
So by taking a plane, it's 2 dimensions.
It's 2 dimensions, yeah.
Okay.
We've eliminated everything above and below in the whole universe from our field of view.
Okay.
So we're not even talking about it, we're pretending the rest doesn't exist. And then we're putting it flat, and we're going to say wherever there happens to be mass in our plane, just whatever happened to be there, what we sliced, we're going to stretch our plane of space down to represent the curvature that exists there. So, and this is a way to get some intuitive understanding of what's going on based on this warped space-time that Einstein said had to exist.
Right.
Okay, why can't we explain warped space-time without getting rid of everything above and below that plane?
Because then we're just stretching into our
Yeah,
third
there's
dimension.
nothing to stretch into,
Right.
right? So
Right.
in order to explain the warp in a flat plane, in 2 dimensions, you needed to use or invent another dimension for it to warp into.
Right.
Right? And if you'd picked a different plane, you would need a perpendicular dimension for it to warp into, but it couldn't be the familiar, say, Z dimension.
It is an XYZ, right?
Yeah, it couldn't be the familiar dimension that you got rid of. It had to be something else. That's kind of vital. That's a step that's usually ignored. In fact, if you look at most of the diagrams of this space-time, if they label anything at all, they'll label the X and the Y of space, and the 3rd dimension doesn't get a label.
Because it's another dimension.
Yeah, and what is it?
It's never been defined
Yeah.
within our system.
And it's been assumed for a long time that that other dimension was a mathematical trick. Okay, it's a trick to allow us to get some kind of picture of what's going on, but that other dimension is required for this other geometry to actually be existing.
Right.
So that's kind of important. So the big picture and the small picture, they're completely not what we've been walking around and having in our heads all this time. We need to really get beyond it. So the key to do that, other dimensions. So how, as we go into that, how do we define a dimension?
A dimension has to allow movement in a
Okay.
direction, or maybe
A space dimension,
a
right,
space
has to-
dimension. Right.
Okay.
So you can move in one dimension without moving in another.
Good. Okay.
And I
so,
used dimension to define dimension, but I'm sure you can do a better job.
Okay, but so a dimension is an independent aspect of our map,
Right.
right? It allows coordinates. If we stick to space dimensions for now, space dimensions are independent descriptors of our map. So you can have a position, and it can be you can have a particle moving along in a direction. Okay. In order for a dimension to be independent of that direction, it must be possible to move in one dimension without moving in the other.
Right.
So if you moved in X, right along the X-axis, you're not moving in Y, and you're not moving in Z. So X is an independent dimension from Y and Z.
Because
Okay.
movement can occur within it without requiring movement
Yes.
in one of those.
Another way to state it is to say that you can't describe position without having all those independent bits of information. So if I wanted to describe a position of something I hid for you to go find, and I told you from an origin we picked right downtown or something, I can tell you exactly how far east of downtown it was. Okay, I've given you, if you want to align east with the X direction, I've given you an X coordinate. Okay, how difficult would it be to find the thing you're looking for?
Very.
Yeah, because I didn't narrow down very much, right?
No.
I've just given you one coordinate,
I
one
don't know where it
location
is north to
descriptor.
south. I don't know where it is
Yeah.
within
Okay.
stories of a building, for
So
example.
if I gave you
Or on top of
now
a
how
tree
far
below
north
you.
and south, yeah, or if I told you how far up above the ground, so in the Z direction also, I could give you those 3 bits of information relative to the origin, and now you know X, Y, and Z. Do you know exact position?
Yes.
Okay, this is exactly what we've been told our whole lives. But in nature, it turns out that we don't have exact information of position with just 3 variables. It seems like it has to be that way.
Right.
But according to quantum mechanics, according to general relativity, that's not the complete picture. So what we want to do is fill in the rest of it. We need to be able to describe how it is that something, if another dimension of space exists, then something must be able to hold still in X, Y, and Z. Okay, so that position I gave you of where the treasure is, it must be able to hold still there and still move in some other dimension. Okay.
Because that happens in nature.
Because that's the definition of space dimension, right? If you're moving in X, you can move in X and Y and not move in Z,
Right.
right? That's why Z is an independent dimension.
Right.
You can move in Z and Y and not move in X, okay? You can pick any ones you want, but it must be, it has to be at least possible to hold still in some and move in the other, and that's what makes the other an independent dimension. We call it orthogonal, and you could reduce it and think of it as 90 degrees, but that's going to make things confusing in the future.
Right.
Okay, so orthogonal means independent motion. All right, so in order to fully answer the question of where these other dimensions are, you would have to have set in your head an answer, a clear answer for how it's possible to not move in X, Y, and Z and still move in some spatial sense.
Which is where my brain just starts to freak out.
Yeah, because we're still stuck in trying to frame the world in 3 space dimensions.
Because I'm having this thought that if you hit an object at the top of a tree east of downtown, and you gave me those 3 coordinates, I could find it.
Yeah,
However, what we're saying is that we have to resolve the big map to the little map, because in the little map, you may not actually be able to find it.
Yes.
And that there has to be one map of nature that describes the entire continuum of
Yes,
what happens.
exactly.
Okay.
To make that a little bit more clear, the object that I'm hiding is going to be an electron. So it needs to be small, because if it's a big object, then all those effects are going to average over, and you're going to pretty much know where it is anyway. You didn't
Right.
need to know exactly where it was, you just need to know close.
Right.
So I'm talking about exact position. Can you define it, which is X, Y, and Z? And it turns out you can't.
Right.
Okay, so we know what it's going to take to be able to answer where are the other dimensions, what are the other dimensions. You have to be able to answer that question in your own head. How do I move without moving an X, Y, and Z? If you can do that, if you can visualize that, then you've got it. Okay, you've figured it out, you've done exactly what everyone's been saying is impossible all this time.
When I have that thought, I feel paralyzed.
Yes. Quantum mechanics, one of the biggest upsets is that they discovered that space and time can only be divided to a certain scale. If you take a region and take everything out of it,
Space is nothingness.
yeah, nothingness is the definition we've all been brought up with, right? Whether we were specifically told it or not, it seems obvious to us. If you take everything out of a region, you have nothing, right? Yet, there's still an associated distance there. There's still this thing we call space. It's not the same thing to say there's nothing there. Yet, we've just intuitively, loosely accepted the idea that space is nothing. And that's where we're going wrong. So,
Because we quantify space by size.
yeah,
so it has a
as a
property.
comparison, but yet, to say there's nothing there would mean, well, why is there still distance? Space gives distance, right?
Right.
If you took everything out, then why is there still distance there?
Right.
Quantum mechanics is studying what space is, and they found out if you zoomed in on a region of space and kept blowing it up by a power of 10 each time, okay, let's say we have a theoretical one that could just keep going as far as you wanted. So every time you blow it up, you take a tenth of what you were seeing before, and that's now the whole field of view, and you do that again and again. Well, eventually, when you get down to what we call the Planck scale, which is 10 to the negative 33 centimeters,
That's small.
that's really small, way smaller than an atom. In fact, if you blew up the whole solar system, if you blew up a hydrogen atom to the size of the solar system, the Planck scale would still be smaller than a hydrogen atom on that scale. Okay?
Say that again. If you blew up a hydrogen atom
To the
size
scale of the solar
of the
system.
solar system.
Now, the Planck scale would be smaller than a hydrogen atom in that scale.
Wow.
Yeah.
Incredible.
So it's
Very
really
small.
withdrawn, but it's not zero. Okay, so there's some scale there, and that's all that matters, is it exists somewhere along the line. So once you approached that scale, you would find the distance between 2 points on the ends of your view. The distance would jump in whole multiples until you got to the Planck scale. It would jump to there's 1 Planck distance between the two ends, and then there's 0, and then 1 and 0, 1 and 0, and you couldn't have anything in between. This means that space itself has structure that only comes in whole multiples of the Planck value.
It has a limit.
It has a limit. You can't keep dividing it.
Right.
When we were investigating the world as humans, as building our practice of science, we used to think a whole set of different things that we think now. Like, we watched water transform to steam and to ice, okay? And our descriptions of what water and ice and steam were entirely different. Now, everybody, well, most everybody, is quite comfortable with the idea that water, ice, and steam are just 3 different phases of the same thing, meaning the same molecules arranged differently, okay? You can't make sense of that until you understand, first of all, that water is made up of pieces, molecules that can be rearranged.
Right.
Okay.
So then they act differently.
Yes, and at one point we did not know that atoms existed, okay, that the world is made of atoms. Here, let's jump to a description of gold. I'm picking gold because a chunk of gold is made of one kind of atom, right?
Right.
Just gold atoms. If we cut that chunk in half and throw away a half, and we keep cutting the half that we're keeping, okay, in half and half and half, we keep going. How long can we do that?
Until we hit a gold atom.
Yeah, okay, so when we have one gold atom, by every definition of what gold is, we still have gold,
Gold.
right? What happens when we cut that gold atom in half, though?
You no longer have gold.
Do we have anything?
No.
Nothing?
Oh, you have pieces of atoms.
We still have something, right? But it
Right.
transcends the definition of gold. So we don't have gold,
Right.
by definition, but we still have something. Okay, the same thing is applying here on space. You can divide space all the way down to the Planck scale, but if you were to somehow have the ability to divide it again, you wouldn't have space. Okay, so the meaning
How?
of space is truncated at the Planck scale. The very definition of it dissolves into something else at that scale, which is something that needs to be investigated. It's something fascinating. Okay, so with that bit of information, with knowing that space-time is somehow quantized, okay, it's got a quantum limit, little independent pieces.
So the Planck numbers aren't something that you just came up with out of your head. This is a natural scale. This
Yes,
is
this
discovery of
is the
nature.
big discovery of quantum mechanics. Yeah. Now let's go back to describing position. Because in nature, you can only go down to the accuracy in space of 1 Planck. If I give you an exact definition or exact description in space of an object, so I've described it down to 1 Planck, there's your location now. I can tell you X, Y, and Z coordinates identify 1 Planck. Now all of a sudden it seems, well, the description's not complete, right? Could it be more accurate?
Where on the Planck?
Where on, in the Planck, something like that. But that information is not given, is not allowed from X, Y, Z information. The best you can do in X, Y, Z information is identify the Planck you're on. Okay, the quantum bit of space. Okay, that's really a big step intellectually to realize, because now we need to address that. So let's just jump into accounting for that and say that it's not a mathematical trick, that this is actually how nature is, that on that scale all of space is made up of pieces, like atoms, like water is made of molecules.
Right.
And it's just on a scale that's so far withdrawn we haven't encountered it yet, but let's just intellectually access that now and zoom in to where we have pieces of space. Okay, here's one, think of it as a bubble, here's another bubble, both of them are pieces of space. If I line up a bunch of these bubbles, I'm now introducing distance between this one and this one. It's the number of pieces between this one and this one, and each one represents a piece of space, which is 1 Planck length in value. If we have just a 2 now in our view, piece of space, what's this between it?
Well, it seems silly to call it space.
Yeah, it would be contradictory by definition to call it
Right.
space, because we just defined this as a piece of space and this is a piece
A
of space.
distance without space.
Yeah, okay, great. So now we're going to have to be more careful and distinguish familiar space. Familiar space is the collection of distance between whatever reference we have and the object we're considering.
Life seems more exciting considering that I'm surrounded by bubbles.
Yes, and as you are
I'm
bubbles.
made of bubbles. I'm in bubbles.
Okay, so now we have to actually use this picture. We're actually already in the picture. We're already visualizing more dimensions, okay? We need to get familiar with how that actually translates. And the only assumption we've made so far is that it is physically real, that on that scale, space is made up of pieces, okay? It's the same audacious assumption to say that water is made of molecules. Now we think it's obvious. When it was made, everyone was really against it.
It's no longer nothing, whereas water is no longer
Yeah.
just a fabric, a consistent fabric.
Yes, a smooth entity. That's exactly what they thought it was. So now we have a map of space that we're building of a whole bunch of pieces. I mean, it's a huge number, right? If we're zoomed in the scale where they're this big roughly though, they're all moving around, bouncing into each other. And you zoom out a little bit more so they're a little tiny. Okay, now you have a region of volume that's a collection of pieces of space, okay? You can define distance from, pick one, pick this one and that one. What's the distance between it? Well, if all the ones are moving around, the distance doesn't stay consistent, right?
Right.
If they're all lined up right like this right now, then you count the number of pieces up and that's the distance between it. But as they move, it shuffles, and if you were just to keep track of the total number, the number would jostle up and down, it would just flicker, right?
Right.
It would go plus 12 and then minus 30, and it'd be back and forth, and it wouldn't be like sliding toward that, it would just flicker. It'd be like quantum mechanics, okay? Where you don't have things that connect smoothly, they just probabilistically change from one to the next. So distance now, familiar distance, like along the x-axis, is no longer smooth and connected and consistent all the time. If you zoom way out, you get an averaging over effect. Like if you pick your one point and another point, and you have billions and billions and billions of points between them, then flickering plus or minus 12, you don't notice, right? You wouldn't register it, it wouldn't be significant to pay
Right.
attention to. So on large scales, all those effects fade away, okay?
They average.
They average over, yeah. So there's our picture, pieces of space, okay? If you identify exact x, y, and z coordinates, you've located one piece. Let's freeze time for now, okay, to investigate our picture. We know which piece we're interested in. We know our location, which means we've given X, Y, and Z coordinates. We know how many pieces of space between our origin in X, Y, and Z to the one we're interested in. So we have 3 bits of information we've identified. And I've given you a position descriptor to do that, but I've only given you now, you're on this bubble. There's other information now available to describe for position. Remember, and you can't move an X, Y, and Z, means you have to stay on that bubble. Okay?
Right.
This bubble still needs to define your position, but you can move inside the bubble, right?
Oh,
You
right.
can move out to any edge, you can move out to the middle. There's a whole bunch of positions now available that don't change which bubble you're on.
Right.
So it doesn't conflict with your XYZ information.
And
It's
this is
new
because
information.
of the Planck constant length. So no matter where in that length you are,
Yep.
you're still in the same point.
Yes, exactly. In the familiar dimensions of X, Y, and Z, you haven't changed anything.
Right.
Because that's as accurate as you could have gotten with X, Y, and Z. But now in this picture, there is more accuracy, but it requires more information. You need to come up with 3 new descriptors to describe the volume of that bubble, of that quantum of space, and where in that volume your exact position is. Okay? And now you have a more accurate definition of position.
And you also have 3 more dimensions.
3 more dimensions. Okay? 3 dimensions make a volume, right? A volume of X, Y, and Z is a collection of all the pieces, right? That map out the X, Y, Z distances. On this scale, we have a volume that's only one piece in space. So it has an X, Y, Z position, but that volume itself is more information. Intraspatial dimensions describe the volume. So yeah, we have 3 more dimensions now of space.
Intraspatial, within the piece of space.
Yes, exactly. Now, there's other information that would allow you to move around in this position. Let's say you've identified you're in the dead center of that bubble. Okay? So now you know your X, Y, Z coordinates, so you know which bubble you're on. You know your other 3 interspatial dimension coordinates, which identify exactly where in the bubble. So that's more accurate information. But what if the bubble was here versus here, and all the nearest bubbles were scattered apart, so you're not switching arrangements or anything. You just move it around a little bit. Does your X, Y, Z information change?
No,
No, because it's just still in the same bubble.
still on the same bubble.
And your 3 descriptors of where you are in the bubble didn't change, right?
Right.
But your information relating how the bubbles are geometrically arranged has never been given to you yet. So we need to be able to describe the volume that's around all the bubbles, the volume that the bubbles are moving through. And when we describe that information, we now know all position information. So you can describe an exact position. Which bubble you're on, where in the bubble you are, how the bubble relates to all the other bubbles. So familiar spatial dimensions, interspatial dimensions, and superspatial dimensions. Okay?
Beyond the pieces of space,
Yeah.
superspatial.
Exactly. So 3 sets of volume. Volume's always 3-dimensional. That's 9 spatial dimensions. We've done the impossible already.
And I'm still in a playland with the balls and the.
Exactly, it's still fun, right?
I can still see it.
And we haven't thrown up any math at all.
Right.
Which is the whole point. We're trying to be able to intuitively grasp what's
Right.
going on, which means it's great to have math to support it. But if the math can't relate to a picture, it's just math still. So we have a picture now. We have all these pieces of space moving around. We've frozen time, so we have 9 space dimensions we've explained. I mentioned before there's 11 total. Well, those other 2 remaining dimensions are time dimensions, temporal dimensions. Okay, we already know one time dimension exists, right? And now I'm saying there's another one. First, let's explain now what time is. Where does the meaning of time come from this picture? Okay, some attributes of time that need to be addressed. Einstein showed us that time has to be related to the familiar dimensions of space. So when space gets more curved, as you approach a black hole, or a star, or even the Earth, that time, the rate of time, decreases. So if you get more space in a region, you get less time. They're offset, they're opposites of each other somehow, okay? Which needs to be explained. Well, it's hard to explain when we don't have an actual rigid definition of time to start with. Here, time needs to be, first of all, an independent descriptor, something that we haven't, everything was frozen to begin with, okay?
Right.
But there's 2 things that if we allow things not to be frozen, they're independent descriptors of what's going on now. Other than just exact position, okay, with the 9 space dimensions, we now let everything start to move. Well, these bubbles, these quanta, are elastic, okay? Let's say it ran into one over here, and now it's moving this way. and it's going to run into something else that's moving in some other direction at some point. But between those collisions, this elastic quanta is going to be resonating, okay, because it's elastic. So all elastic spheres would do that. Every resonation is information. The total number of resonations is something that isn't described by just describing position, right?
Right,
If I've told you
right.
exact position,
New information.
yeah, you had no information of how many times the things resonated.
Right.
So if you keep track of how many times each piece of space resonates, then you now know how much it has aged through time. Time actually is those resonations, okay? So-
Time is the resonation of a piece of space.
Yes. And some magical trick just happened right there, because the problem quantum mechanics has had with trying to address time in their equations is that general relativity requires that time must be able to be defined uniquely at each point in space. And here, it's automatically defined uniquely at each point in space. This one resonates based on how it's run around and everything else. And this one right here, completely independently,
Right.
right? They're all aging on their own, in their own way. If you zoom way out or you look over long scales, if the density is the same everywhere, then pretty much everything runs into something else on average the same amount, and they all average. But on the small scale, none of them average the same. None of them age the same.
Right.
Okay, if energy is being carried by one piece of space, it's moving through and it's resonating, it's going through time, so it's moving through time, okay? And now the energy hits this other one, and now it's carried like a collision of a billiard ball, okay? Elastic
Right.
collision, and now it's carried onto this one. And now this one's going like this. Of course, this one's still doing this afterwards. During the collision, however, that energy doesn't move through time, because this thing is not independently resonating.
It's not resonating.
Yes.
Right.
So the energy
Okay.
only moves through space or moves through time. It doesn't get to do both. So if you have a region now where you pack all the pieces of space tighter together, and energy is trying to move from one piece of space to the next, it's not going to age as much.
Right. Less time.
Yeah.
Fewer resonations because they're packed, so they can't move as freely.
Great. Okay, so our definition of time automatically now has allowed us to define why time, well, how time, first of all, is uniquely defined at each location, at each point in space, but also, from the same explanation, why time would slow down as you approach a black hole. Like the two biggest mysteries of time are just part of the natural picture. Okay.
They're inherent.
Also, we're explaining now what a black hole is, right?
Right.
Or any gravitational field. It's a change in density of the quanta of space from one region to another. If you pack them together close over there and they get less and less packed as you get away, that change in density is the gravitational field. It's what the black hole is. It's the distortion that matter causes. That's one time dimension. So information of how much each piece is doing this. Okay? That information, the number of resonations, doesn't tell you anything about the motion through the superspatial dimensions. Right?
Right.
Velocity, for example, is a description of how fast something's going, which means how much space it moves in how much time.
Right.
Without a descriptor of space and a descriptor of time, you can't have meaning for velocity. Here we have pieces moving through superspace. Okay, it's moving through some sense of space, the volume that we define as superspace, and and you can see it moving, which means it has a velocity. But you have to define the time in that superspace in order to make sense of that velocity.
Right.
So here we have two independent descriptors of time, one that uniquely exists with each piece of space, the resonations, and one that allows you to define motion in superspace. Okay, so 2 time dimensions, 9 space dimensions, we're at 11 dimensions for our map of the universe. Now everything falls together really quickly. I want to get some kind of feedback on how clear was that, what part's confusing or which part is just like, okay, well, I'm really seeing where this is going.
I can see the picture. It's a picture in my mind.
Great.
So it's
That's exactly what we're going for.
I can see the pieces and I can see the space between them and I can see that within each piece there is space as well. And they're moving on their own and they're moving through what is now superspace,
Mhm.
bumping into each other, and it's very visual. I can see it.
Yeah, the whole thing at once too, right?
Absolutely.
And you also, I'm assuming, because I do, have the ability to zoom out in your head and keep track of what's going on,
Right.
right?
Yes.
I mean, just zoom out, you just change scale and it didn't get
Mhm.
confusing. All right, this is great. Okay, let's go into, we have understanding of all the 11 dimensions now, and the only thing that got us to that picture was assuming that the quantization of space-time was real, was physically real, and addressing what that meant.
Right.
Okay, So there's our one assumption. Let's see if our assumption leads us to something that's valid. It gave us a definition of time. That's cool, because our definition automatically required the big crazy aspects of time, right? Why would time would slow down? We can even address if you speed up faster in space, keep going faster, fire rockets more and more, so you're approaching the speed of light. Einstein's special relativity showed us that time also slows down for you, okay, relative to other people who are going slower. Why in this picture would that be the case?
Because time and space are inversely related.
Okay.
So as you're speeding up, you're going through more space. You're experiencing more space.
Which means you have to experience less time.
Less time.
More collisions mean less free resonations.
Right. Perfect.
Okay, good. So the mysteries of time is just dissolved away, and we have a simple definition that it's not confusing, which is exciting for me. All right.
And everyone else on the planet.
It's got to
if they're
be.
awake.
Yeah, it's got to be. Because now we can actually start new discussions. Discussions that were just purely philosophical for thousands of years, we can now readdress.
Right.
All right, so let's return now to black holes and gravity and see how this picture explains what gravity is, what black holes are inside the event horizon. So let's do gravity. If something's orbiting something else, because gravity has this pull on it. Well, first let's say you're the thing that's orbiting. If you're an astronaut out there floating around by yourself in a suit, and gravity's pulling you towards Earth, right? Which is why you're always falling toward Earth. This is why you orbit around instead of just going straight and getting further away. Do you feel gravity pulling on you?
No.
So is anything actually pulling?
No.
You're right. Good.
Okay.
So this idea of gravity pulling objects together is an artifact of our three-dimensional conception. Right? We had to invent that idea. There's the moon orbiting around. Here's Earth, obviously fixed right here. Something has to be pulling the moon towards Earth in order to make it go in the path it's going. But the moon doesn't feel itself being pulled.
Right.
Nothing that orbits feels itself being pulled. There is no force pulling. Okay?
How amazing. So there's no force of gravity.
Exactly.
Okay.
The force of gravity is something we invented to make up for the mistakes of our three-dimensional picture. In the 11-dimensional picture, you didn't ever need to invent it. Okay? If you kept track of the actual structure, the arrangement of all these quanta of space, you don't need to invent the force of gravity. Motion that we blamed on gravity before is automatic in the same way. Okay, let me explain why.
Good, because I'm getting angry with my physics teachers.
Good, you should. In this picture now we can have density gradients of space. The pieces of space can be packed together in one spot. Let's say over on this side of the room. They're packed together really tight, and they get less and less packed as we get to the other side of the room. Okay, so there's
changes in density.
Change in density. That's what I mean by density gradient. Just like the air. There's higher air pressure down here than at the top of the mountain or straight above us, a mile or so. Okay? There's less air per cubic meter. So it's packed together tighter here than it is up there. If you're an object with some length, just pick your own body, and you stretch out your arms, and you're going this way, but you happen to be going through this region where there's this gradient. There's some black hole over there, and as you approach the black hole, there's spaces packed closer together. Let's try to figure out your motion. Now, we don't need to explain straight motion, right? If something's going straight, it keeps going straight until a force acts on it.
Right.
If something just continues to go straight, there's no mystery there. If it changes its direction, if something all of a sudden, if it moves, then you're like, well, something made it move. Something made it not go straight. We need to explain what that thing is. Going straight means what, if I were to relate my left hand and my right hand as I'm moving?
You're covering the same distance.
Yes. So my left hand experiences the same amount of space as my right hand on average.
Right.
Right? So if it didn't, if my left hand experiences more, then I turn.
Right.
If my right hand experiences more, then I turn. That's not going straight. Well, here, we're now going through a region where there's a gradient of space. Denser over here, less dense over here. What's the straight path now?
It's denser over here, so you're going to be curving this
Yes.
direction.
In order for this one to experience the same amount of space as this one, it needs to go that way.
Right.
But that way is still straight, because it's the same amount of experience of space for both sides. So the straight path through curved space is the orbit. You didn't need to invent some magical thing pulling it or anything. It's just going straight through curved space.
That's amazing. So there is no force.
No, There's no magical force of gravity pulling things towards each other. It's not there. It's a disconnect of the structure of space. If you think space is smooth and consistent everywhere, then you need to invent something to make that motion.
Right.
Let's approach the black hole now. Let's just zoom in towards it, get closer and closer to the black hole. What are the pieces of space doing in their arrangements as we get closer and closer?
They're packed more tightly. So
Okay.
there are fewer
Is there a
resonations.
limit to how much they can be packed?
Just down to the Planck length.
Yeah, until there's no more superspace between them.
Right.
Right? So they can be, there's a closer than this, but then they get closer and closer. And if all of them are now touching,
They're touching. Right.
all of them have no superspace between them, you can't pack them anymore. When that happens, you have a black hole. A black hole, a supermassive one, is a whole bunch of quanta that are stuck all the way together. Okay, which is really easy to picture, right?
Right,
Very
yeah.
simple.
Yeah.
And we need to, one of the mysteries of the black hole is there is no time in a black hole. In fact, you can say a black hole is purely space-like, no time. Does it make sense in this picture?
Yes, because if they're all touching, they cannot resonate.
Yeah, they can't freely resonate
Clearly, there's
if
no
they're stuck
movement.
together.
Right.
So there can't be time experienced in a black hole. There can only be space in a black hole, which is the requirement of the definition.
Oh.
Okay, so the gradient that comes out of the black hole, the change in density, is what makes it so things that are moving along and coming to that region orbit and they appear to change their paths. That's their actual straight path, which is why light, when the gradient gets so steep, light can't even escape because the straight path is toward the black hole.
Into, right.
Okay, so those are the mysteries of black holes, right? We can now visualize, we can conceptualize what a black hole looks like all the way to its interior. Notice also, though, we got beyond that little fallacy that a black hole is zero size, which didn't make sense to begin with. Now, it's an amalgamation of a bunch of quanta, a whole bunch of them stuck together, okay? So effectively, it is one quanta, by effect, not in reality,
Right,
but by
right.
effect, that all of them
How
act
it
together.
acts.
Yes. So you could say, based on its behavior, its size is one quanta because it acts that way. But if you make a bigger black hole and squeeze a couple more on there, it's now bigger. And the
Uh-huh.
gradient extends out further, right?
Right.
And you get one that's more massive, so it has more gravitational effects. Okay, so it isn't zero size. In fact, there is no such thing in the tapestry of space-time, a familiar space of zero size. The smallest you can have is a Planck length, okay, one quanta of space. If you have less than that, you don't have space. So it's not zero size, it's beyond the meaning of size. We actually covered black holes already. I mean, it's done now, right? That's the whole picture.
That was easy.
Yeah.
Yeah.
Okay, big mystery taken care of. Quantum tunneling, one of the ones we talked about before. How is it that things can disappear from the fabric of space-time and reappear somewhere else without ever interacting with any of the pieces that we think are between those two locations?
Because if you're on a single piece and you don't jump to another piece of space, then you can move through the fabric of superspace and not
Yeah.
and stay
There's somewhere else to move. Huh?
right, right.
So if you're huge, what's the chances of you moving from one region to another region and a whole bunch of spaces between it?
Not very
Good because the pieces are all moving around. So
Right.
you're going to register as being somewhere as during that
Right.
motion. If you're small, it's possible for you to move right through it without ever interacting with any of the pieces, so you never registered an interaction with any location in space. So as far as the observers are concerned, you disappeared from the fabric of space-time until the next time you register, until the next time you interact with a piece of space-time. And now there you are. You now have location again in the familiar dimensions of space. Okay, so quantum tunneling, easy mystery to solve here. One of the big parts of of the mystery of quantum tunneling is why is it that it happens on the small scale and fades out on the large scale? What determines that scale? Here, it's the pieces of space, the size of the pieces of space
Right.
that determines it. All right, so we've covered a lot of ground with one simple picture that you just got right away, right? It's all clear in your head?
I have a beautiful picture of these iridescent bubbles floating through superspace, resonating.
Perfect.
Yes.
And that picture is 11-dimensional. Very simple, very beautiful, and we just did the impossible. So as evidence that we did the impossible, we solved from that picture and got an intuitive explanation for time, for gravity, black holes, and quantum tunneling.
Yes.
Okay, there's a whole bunch of other mysteries in physics that naturally pop out solved from from that picture. A short example of would be dark energy, dark matter. What are they? Where do they come from? What do they form? Why do they exist? All that stuff naturally comes out as a requirement of our new picture. And Heisenberg uncertainty, okay, which is a dominant principle of quantum mechanics. So and there's many more, and they're all covered in my book, so we can go over them in great detail. But you've already got the whole picture in your head. You already see them in 11 dimensions. You made the big step, and now we can start seeing the world in a new way.
How beautiful. Thank you, Beth.
Yeah, thank you.